Hello, everyone. As promised, I'm going to now prove the following result, the following proposition, which is that the outer measure of a closed interval a to b is just the interval's length b minus a. And as I mentioned, this is actually, in my opinion, one of the trickier results I would say in really the whole course. To me, this is one of the trickier results. But yeah, so let's go through it. So let's do one thing, get kind of the easy half of this proof out of the way. So let's say epsilon is positive. Okay, so let me just write down, remind you what the definition of outer measure is. So maybe I'll first write the definition down and then give you an epsilon. So remember this here is the infimum of all possible sums of lengths bk minus ak, where a to b is a subset of, well, the union here. So these intervals cover a to b. All right. Okay, so let's say epsilon is bigger than 0. Trivially, a to b is a subset of the open set a minus epsilon, b plus epsilon. So we have an open cover of a to b. Okay. And if I didn't mention this last time, when I write this, implicitly, I'm allowed to assume that this is finite also. We're considering both finite and infinite covers here. In particular, to get, by this definition, to get a finite cover by intervals, after a certain point, you could just declare AK to be equal to BK, and so you basically have the empty set. And you really, the length of that empty set is 0 by definition, essentially. But yeah, so really, when I write this here, I'm also allowed to consider finite unions here. Okay, right, so I have an open cover of A to B. So m star is the infimum of all these possible lengths for all possible countably infinite or finite open covers by these intervals. So the infimum is less than or equal to the sum of, well, the length of this covering interval, which is b plus epsilon minus a minus epsilon, which is, of course, just b minus a plus 2 epsilon. And this is for arbitrary epsilon. And henceforth, we have half of our theorem, or half of our proposition. So certainly this half is not one of the trickier results in this course. All right, so it's the other half that is rather tricky. So when I write ETS, that means it is enough to show. So it's enough to show that we'll just prove the other half. So it's enough to show that this is bigger or equal to b minus a. Okay. So how are we going to do that? Well, again, we're going to use the definition. Let's say I have an arbitrary cover of a to b by open intervals, finite or countably infinite. And again, the case where this is finite, you can just get by, after a certain point, just setting AK to be BK, so you have the empty set, the empty interval, if you will, and we're allowing that to count as intervals. The length of the empty interval is 0. So let's say this covers A to B. So what do? We need to show, that this sum here is bigger or equal to b minus a. Okay, and if we can do that, that will imply that m star of A to B is bigger or equal to b minus a. Why? Well, it's just a definition. Okay, so let me explain that if it's not clear. So we picked an arbitrary cover and we looked at the sum. What this proves here, because this is AKBK is arbitrary, it's just an arbitrary cover of A to B, B minus A is therefore going to be a lower bound for all of these sums of all possible, all of these sums of lengths of covers of A to B, okay? Well, B minus A then is a lower bound for this set here. The infimum is the greatest lower bound. So the greatest lower bound is bigger or equal to this particular lower bound, which is exactly what I need to show. So that's really our task for just some arbitrary open, countable cover of A to B, countable or finite cover of A to B of open intervals. We need to show that this sum here, the sum of the lengths, is bigger or equal to b minus a. Okay, so what we're going to do is use the Heinen-Burrell theorem, which just says A to B is compact. I presume Professor Pachanu went over what Heinen-Burrell says, but if not, I'll explain it in a second. So by the Heinen-Burrell theorem, sorry about that, there exists a natural number n where A to B is covered by a finite number of these intervals. So we have an open cover that covers a closed interval. The Heinen-Burrell theorem says that whenever we have that, we can always pick a finite subcover. That's exactly what this means. Okay. Or in other words, Heinen-Burrell theorem says A to B is compact. If Professor Pachanu never used that word, then that's okay. Okay, so this is really the key here, as we'll see in a moment. And I should mention, I'm basically doing the same proof as the book. I'm going to do things slightly differently. I think I'm going to be, if I might say so myself, a little clearer than the book. But for all practical purposes, it's basically the same proof. Okay, so So what are we going to do? We're going to show that, in fact, this sum here is less than, we're going to show that this sum here is, in fact, bigger or equal to b minus a. That'll certainly finish up the proof, if we can do that. Okay. So let's assume, and here this is where I'm differing from the book a little bit. I think it's clearer to do this proof as kind of a, almost like a proof by contradiction. Assume this is not true. Assume that this sum here is less than b minus a. Okay. Okay, so yeah, so I'm going to do a step-by-step procedure like the book does. So step 1, kind of formalizing this procedure by induction will be homework that I will assign and collect in the next homework. Implicitly, the book is doing this inductively too. Right. So obviously A is in A to B. So A is in one of these intervals. So A is in this union here. So let's pick, I'm going to use subsequence notation. I don't know if there's any particularly good notation to use, but so let me pick, I'm going to call this AK1, BK1. This is a very special interval. It's something, it's one of these intervals here that contains the point A. Sorry about that. Okay. Right. So obviously this means, I don't think there's any doubt here, that just means AK1 is less than A is less than BK1. Now, if you want to draw a picture, that's okay. I'm not really sure it is too helpful to draw pictures, because really just the picture gets so complicated that it's of no use. So I'm not going to do it. But anyway. Okay. So let's assume that B is less than or equal to BK1. Okay. Either B is bigger than BK1 or B is less than or equal to BK1. So I claim this is impossible. If this is true, then this length here, BK minus AK, is certainly bigger or equal to BK1 minus AK1, because this interval is just one of these intervals here. I mean, in theory, it could be equal. Really, this n could be 1, or even, I guess, technically, we could have, we could have one genuine interval and the rest the empty set, something like that. But certainly, it's bigger or equal to BK minus AK. Now, so what do we have here? BK1 is, we're assuming, is bigger or equal to B. Well, A is bigger than AK1, so minus AK1. Right, sorry, minus AK1 is bigger or equal to minus A. Again, AK1 is less than A. It's actually less than, doesn't really matter. Yeah, AK1 is less than A, so minus AK1 is bigger than minus A. Okay, so this is, well, it's bigger, but we don't really care about that. It's in particular bigger or equal to B minus A. And, well, we assumed sorry about that. Yeah, so we're assuming this is true. And let me call this star here. I'll give it a name. So this violates our assumption that the sum is less than B minus A. Okay. So what does that mean? That means, this is a no-no. B is bigger than BK1, right? So let me go on the next page. So that means B, and I'll write it like this, BK1 is less than B. So there's going to be a lot of A's and B's floating around. If anything, I would just go back and rewatch the video and yeah. I mean, if this is a little convoluted on a first viewing, that's okay. We do arguments like this in analysis, inductive arguments, so it's good to really understand that. And besides, homework is based on this, so just for that reason alone, it's good to understand this. Okay. So let's kind of summarize everything we know so far. So I'm going to use this, so I'm going to put this in a box here. And I'm going to use this here, so I'm going to put it in a box. So AK1, so just combine the two boxes here. Well, the first box gives me this here. And this box here says this is less than B. And so what on earth is the point, you might ask? And that is a good question. The point is right here. Okay, BK1 is between A and B. Okay. So now we can perform step 2. So at each step, I'm getting a new interval. Okay. So just kind of reiterate, just being a bit redundant here. If that annoys someone, I apologize. But yeah, so this is saying what's in the yellow, saying BK1 is between A and B. So so let's pick K2, or rather, let me do it like this. Let's pick one of these intervals. So remember, well, sorry. This is true. Right. So, I mean, what I've said is this is absolutely correct, but really, yeah. So, in particular, this is true. So, right. So, the AK, BKs cover A to B. So I can pick one of these where BK1 is in this interval. Again, because BK1 is in A to B, and A to B is covered by these n intervals. Sorry about that. BK2. So in other words, BK1 is in A, K2, BK2. Okay. Right, so I'm going to use this in a moment. So something important to note is that, well, we have two distinct intervals. Okay. And if that's not clear, it's probably not clear because it's almost like a Where's Waldo. It's like staring right at you. I'll explain that in a second. When I say, sorry, it's like a Where's Waldo book. It's you know, Waldo is right in front of you and you might not be able to see it. Well, that's because I'll put this, I don't know, sure. That's just from right here. So these two intervals cannot be the same because BK1 is less than BK2. For two intervals to be the same, two open intervals, you have to have both endpoints being the same. Okay, so, all right, so yeah, so we're going to continue on. So let's look at B and BK2. I want to assume that B is less than or equal to BK2. Okay, let's see what happens here. Well, K equals 1 to N, BK minus AK is certainly bigger or equal to, I have two distinct intervals among this collection. So the sum of all these lengths is bigger or equal to the sum of these two lengths for these two distinct intervals. Now we'd be in trouble if you know the same interval was repeated. But it's not, so we're safe saying this. BK1. So let me rewrite this in a bit of a funky way. BK2 minus AK1 plus BK1 minus AK2. So I claim that this here is bigger or equal to 0. Well, there's not much to that. That's exactly. So I have to admit, one of the things I like about doing this, I guess I could always just bring colored chalk with me, but it's quite easy to use colored chalk and use various colors, which I think really makes particularly this proof much more digestible. Anyway, so right here says AK2, or sorry, BK1 is bigger than AK2. So BK1 is bigger than AK2, so this is bigger or equal to 0. All right, so I guess I'll leave it. Okay, well, we're assuming B or BK2 is bigger or equal to B. And actually, again, doesn't matter, but really it's bigger. This is bigger, I guess whatever, I'll stick with black. This is bigger than B. And let's go back a bit. again, as before, minus AK1 is bigger than minus A. Okay, so this is bigger than B, bigger than minus A, bigger than 0. So in particular, this is bigger or equal to B minus A. And that's, again, is a violation of our assumption. So just a tip, if you do have access to a printer, it might be a good idea to print screen and print some of these pages off. So that you can kind of refer back to various things I put in boxes that are useful. Okay, so just like before, we have basically the same conclusion here, but for B and BK2. Sorry. So yeah, this is not true. So BK2, BK2 is less than B. All right, so I'll do this one more time. So now we're at step 3. Okay, so we're going to define our third interval. Now, obviously, this is inductive in the sense that intervals are defined in terms of previous intervals, but it should be clear. Or if it's not clear, it'll be clear in this step, I think. Okay, so well, what do we have? Let's see, what do we have? Right, so right, so let me we have AK sorry. 1 second. Yeah, it is a bit easy to lose track of kind of what's important here. Okay, yeah. So from step 1, remember that we have A is less than BK1. That's what's right here. A is less than BK1. Okay, so from step 2, we have, I guess I'll get rid of this. We have BK1 is less than BK2. Well, I guess technically from step 2, we have BK is less than B. That's just basically what we just proved. Basically, the last thing we proved is that BK2 is less than B. Okay, so again, why does that matter? Who cares? The main point is that BK2 is between A and B. It's strictly between A and B, but it's in particular, it's in the closed interval. Okay, so right, pick let's call it AK3, BK3. Just pick one of these intervals, any one of these intervals among the AK, BKs. Again, not to sound like a broken record, but these intervals cover A to B. BK2 is an A to B, so we can always pick among these n intervals one of them where BK2 is in this interval. let me move that up a bit. Let me do it in the next page. I don't know. The Zoom whiteboard is always slightly smaller than I think it is, which can have disastrous consequences. Maybe disastrous is a strong word, but undesirable consequences. Okay, so yeah, again, in other words, BK2 is an A K2, sorry. BK2 is an A K3, B K3. Okay. That's exactly how we, well, that's exactly how we're picking AK3, BK3. We're picking it so that BK2 is in it. Okay, so fine, I'll do this one more time. If B is less than or equal to BK3, then the sum here, well, so I guess before I do that, I just kind of make a note here. Again, we have BK1 is less than BK2. BK2 is less than BK3. So we have 3. You might be able to see where this proof is going. If not, that's okay. So these are 3 distinct intervals. Again, if you have any 2 intervals being the same, they have to have the same endpoints. Whoops, that doesn't make sense. This does. Yeah, BK1 is less than BK2 right here. BK2 is less than BK3 right here. Okay, so we have, yeah, so in particular, the right endpoints of these intervals are all different. I mean, in theory, we could have the AKJs are all the same, but that's fine. We just have 3 distinct intervals because the right endpoints are all different. Okay. All right, so last one before I just write down the induction, which, yeah. So again, assume that B is less than or equal to BK3. Okay. So what happens then? So, excuse me. K equals 1 to n. The sum of these lengths here. Again, we're just picking out 3. We're picking out 3 distinct intervals among these n intervals. So it's j equals 1. Yeah. J equals 1 to 3. So the sum of all these intervals is just big or equal to the sum of these 3 distinct lengths of these intervals, or the sum of these lengths of these 3 distinct intervals. Okay, so right, so let's write this out in the following way, and I'm going to do it this way. Kind of give you a little hint when doing the homework. So it's j equals 1 to 2, b, k, j minus a k j plus 1. And just if there's any doubts, this is going to be b k3 minus a k1 plus b k2 minus a k3 plus b k1. Sorry about that. K equals, when j equals 1, rather, it's bk1, ak2. And when j equals 2, it's bk2 minus a k3. Okay. So for the bk's, we got bk3, bk1, bk2. For the a's, we got minus ak1, minus ak2, minus ak3. So yeah, this is correct. It's just a funny way of writing it, but there's method to this madness here. So I'm going to erase this. Right. Well, we're going to write it this way so that we can get this to be bigger or equal to b minus a, okay, which is again, contradiction. So each one of these is bigger or equal to 0. In particular, bk2 is bigger than ak3, so this is true for j equals 3. ak3 is bigger than, bk2 is bigger than ak3. I'd be in trouble if ak3 was bigger. No, it is bk2 is bigger than ak3, so this is bigger or equal to 0. And we already did j equals 1, but I'll just remind you that bk1 is bigger than ak2 by step 2. bk1 is bigger than ak2. So this is true for j equals 1. So for each j, this is bigger or equal to 0. Well, again, we've did this many times. This is bigger than minus a. And this here we're assuming is bigger or equal to b. Okay, so this is bigger. It's bigger, really, but bigger or equal to b minus a plus positive stuff. So it's bigger or equal to b minus a. And again, this violates okay, so enough's enough. This should give you a flavor of what's to come. Okay, right, so by induction, meaning you should do this for home, meaning it'll be a homework I'll collect. We haven't proved this. We actually proved this for n equals 1 and 2. Yeah, we've proved this for big N, 1 and 2. Really, for the induction, you just need n equals 1, but n equals 2, I think, makes things a lot more clear, even though it's technically not necessary. So for any natural number n, there exists, essentially just intuitively continuing this process, but I do want you to carefully prove this by induction. So just like in 511, we do need induction proofs in analysis. Okay, so by induction, for any big N, any natural number big N, we can find intervals among this collection of intervals where the following is true. Well, first of all, we absolutely need this to basically get started. A is between A, K1 and B, K1. So that's kind of our first thing. And a second is just what we've had before. AKJ plus BKJ is basically between AKJ plus 1 and BKJ plus 1. This is for all j between 1 and n minus 1. Okay. Okay, so, oops, didn't mean to do that. Sorry about that. Okay, so what does this mean? This means, in particular, that because this is true for all j between 1 and n minus 1, we have, I'm being redundant, but I just want to make sure everyone is clear here. Just do this, for all, because this is true for all j, what this is saying is that the b's are strictly increasing. So again, this is a collection of distinct intervals. Each one of them is one of these intervals here. And this is true for all big N. Now that should look a little funny. That should kind of, alarm bells should be going off here. Okay. Well, that should, the alarm bells, right, so let me write it like this. This is impossible. Well, this is impossible for big N bigger than N. So there's nothing wrong with this. By our assumptions, there's nothing wrong with this induction claim. Or rather, there's nothing wrong with this statement here. This is a correct, true statement by our assumptions. But that leads to the absolutely absurd conclusion that, in fact, this this cover, which has n elements, in fact, has at least big N elements for every single natural number n, so it actually has to be infinite. That's absurd, okay? So what's going on here? What's going on is star here, okay? So this cannot be true. Okay? If this is true, then we're essentially violating Heinen Burrell. We're essentially violating compactness. We're essentially saying, in fact, we're constructing a violation to this here, that there exists an n where this finite number of intervals covers A to B. Okay. This statement here is really forcing this to be infinite. Okay. So this is false, the star here. Okay. This cannot be true, and hence this is bigger or equal to B minus A. Okay, so we just proved that the outer measure of a closed finite interval is its length. And based on that, the homework that I assigned is that the outer measure of any finite interval is just its length. So let's finally prove that if I is an unbounded interval, then the outer measure is infinity. Okay. So let's say, just for example, I equals A to infinity. Okay. Right, then we certainly have that, let's say, so let's actually do, yeah, I can do this. So we have that for any large n, we certainly have that, well, let's assume what I'm asking you to prove for homework is true, and in particular that the outer measure of a finite open interval is its length. Okay. So in particular, we have for any natural number n larger than a could be just any real number whatsoever, an is certainly a subset of a infinity. So we proved actually before, that means that the outer measure of a to the n, which is just n, sorry, that's n minus a. That's less than or equal to the outer measure of my interval, my infinite interval. Okay. And this is true for any integer n larger than a. So that means pretty obviously that this interval here, the outer measure has to be, well, it has to equal infinity. Meaning that it's bigger or equal to any real number whatsoever. Okay. All right. And by basically the same reasoning, we have m star of, I just don't like double brackets, so that's why I'm not putting it here. A to infinity. This is also infinity. Doing something like minus infinity to a. Well, that's also infinity. I'll just write like that. And same thing for closed here. If you have a closed here, this is also infinity. All right, so let me get out of the way two fairly easy properties of outer measure. Very important properties, but nonetheless pretty straightforward properties. So, right, so first, I claim that our outer measure is translation invariant. And Right. So in other words, for any x in the real numbers, any real number x, the outer measure of a plus x for any set a is the outer measure of a. And I told you what this was before, but I just want to remind you this is a set of all little a plus x, where little a is in big A. Okay, and yeah, I'm following basically the book's proof, filling in quite a bit of detail. The book is very terse on this proof, I think, a little overly terse, but anyway. Okay, so given any subset A of the real line, we have A is a subset, or A is covered by these intervals. If and only if A plus X, I don't know why I keep doing A times, whatever, I keep forgetting the plus. But anyway, if and only if A plus X is a subset of, just move these intervals by X. And by that I mean we take AK plus X, BK plus X. Okay. Right. And this is just, yeah, there's not much really to this. Just check yourself if there's any doubt. So what does this mean? Well, the outer measure of A is the infimum. I'm just rewriting the definition here. And again, this could be a finite sum if we have a finite cover. Okay, well, as we just what I just mentioned, A is a subset of these intervals cover A precisely if, if and only if, precisely, in other words, when A plus X covers, when A plus X is covered by AK plus X, BK plus X for all integers K, all natural numbers K. Okay. So in other words, we have equality here. Because we're dealing with exactly the same intervals. Okay? These intervals, AK, BK, are exactly the same. So again, for AK less than BK, for each K, these intervals AKs, these intervals AK, BK, cover A if and only if AK plus X, BK plus X covers A plus X. Sorry about this here. Okay, so in other words, this set here that I'm circling is equal to this set here. So in particular, the infimums are clearly the same. Okay, but I can do something a little seemingly silly here. Just basically add and subtract BK from this each term here. So just write this as bk bk plus x ak plus x. Okay. Otherwise, yeah, so literally these two are exactly the same. There's really nothing to this here. All right, so just rewrite this. I forgot the k equals 1 here. So ak plus x, bk plus x. Okay, and last but not least, if let's say, let me get rid of this here. If I set, let's say, this here to be a k prime, b k prime, okay, then we have that this is going to be equal to, need another equal sign, sorry about that. Okay. And I'll explain this a little bit more in a moment. So it's bk prime minus ak prime. It's up a bit. Where a plus x is a subset of, or is covered rather by ak prime, bk prime. So again, the point here is more that what I'm putting in a rectangle here, this set equals this set here. Okay. And if there's any doubts, just check one is a subset of the other and vice versa. Okay. Yeah, so this red boxed in set here is equal to this red boxed in set here. And henceforth, the infimums are the same. And of course, really, this is the definition of the outer measure of a plus x. Okay. Okay. Right. Okay. So again, the punchline here is really that, forget about infimums, this set here equals this set here. Okay. And then, well, henceforth, the infimums are equal. Well, just add and subtract x to each term. These two are equal. And this set here, forget about infimums, equals this set here. Hence, the infimums have to be equal. Okay, right, so outer measure is translation invariance. So let me finish off by proving a very basic fact about outer measure, which is called countable subadditivity. So countable subadditivity says the following. If we have a sequence ek of subsets of the real line, and we want to take the outer measure of its union, then we can say, at the very least, that this is less than or equal to the sum of the outer measures. Yeah, as I mentioned, this is called countable subadditivity. Okay, and the way you should think about this is if you've taken a undergraduate probability course, you'll probably remember that the probability of a union is less than or equal to the sum of the individual probabilities. It's usually not going to be equal unless you have disjoint events. And in general, for like the union of 2 events, the union of 3 events, you have actually explicit formulas for computing the probability of the union of 2 events, the union of 3 events. It's a bit messy, but certainly, yeah, the probability of a union of events is less than or equal to the sum of the probabilities. Okay, and really that you should kind of, this is very analogous to that. Okay, and I should mention from this proposition, you can prove. I'll leave that as a homework. I don't know if I'll collect it or not, but you can prove finite subadditivity. All that means is the outer measure of a finite union is less than or equal to finite sum of the outer measures. Okay. Yeah, I don't want to say more than that, but all right. So before I prove this, I want to mention a note from basic analysis. And if you did not prove this, it's probably just because there's a lot of other stuff that needed to be proved, perhaps more important, more immediate, of more immediate concern, and there just wasn't enough time to do it. Okay, so if I have non-negative numbers a, I, k, for each pair of natural numbers, then the following iterated sum is going to be equal to the following sum here. For any bijection from the natural numbers to the natural numbers times itself. Okay, and yeah, this makes sense. I mean, this red sum here, this red sum here is simply adding up all these a's, because phi j, as j varies, captures all pairs of natural numbers. It's bijection, so it's surjective, and there are no repeats. Okay. So the red sum is exactly just adding up all these a's for all pairs of natural numbers. And intuitively, that's what the iterated sum gives you. It really kind of gives you the same thing. Technically, it looks a little different, but as long as we have, in general, this is not true, I should say. This is in general not true, but as long as we're dealing with non-negative numbers, all is well. And it doesn't matter if any of the sums are infinite. That's still fine. All right, so let's put this to good use and prove countable subadditivity. Okay. So let's say epsilon is bigger than 0. Let's use the definition of outer measure. So by definition, I can pick for each fixed k integers sorry, I think I said integers. I can pick intervals for each fixed k covering ek, where the following is true. So the sum of these lengths here is less than or equal to the outer measure of ek plus epsilon over 2 to the k. And why is this true? Well, remember what outer measure is. It's the infimum of all sums of lengths of intervals that cover my set, ek. And when I say that, I mean we're only dealing with countable or finite coverings of ek by open intervals. Okay, so in particular, add epsilon over 2 to the k. Well, the infimum is the greatest lower bound. You add epsilon over 2 to the k, it's no longer a lower bound. And hence, there is a covering where this is true. Now, you really need less than or equal to. If the outer measure has if the outer measure rather is finite, then by definition of infimum, it's possible to pick this so that it's less than. But if the outer measure of ek is infinite, then that means that for every covering of ek, the sum of the lengths is infinite. That's exactly what it means for outer measure to be infinite. So really, to take that as a possibility, we need less than or equal to. Not a big deal. On a homework, if you just put less than, not the end of the world. Okay. Okay. Right, so what does this tell us? Well, first of all, it certainly tells us that if we just look at all of these intervals, then they cover the union. That's pretty straightforward. So we have a countable covering of the union by open intervals. Now we can use, once again, the definition of outer measure. The outer measure is the infimum over all possible sums of lengths of coverings of the union, rather, by open intervals. We have one particular one of them. So then the infimum has to be, it's a lower bound. So the infimum is less than or equal to, well, the sum of the lengths of all of these intervals. What do I even mean by that? I mean exactly this red sum here. Where here, aik is just the length of this interval here. Okay. So here we're setting aik to be bk minus aik. Okay. Right, so this red sum here for any bijection is exactly the sum of all of these lengths for all pairs I and k. And this note says that this is going to be equal to this iterated sum. Okay. So this is less than or equal to this red sum here, which is equal to the iterated sum. first doing k, then doing I. Sorry about that. And I should make that summation look a little nicer. Okay, but we know that the inner sum is less than or equal to m star of e to the k plus epsilon over k. And you should be able to see where this is going and why we needed epsilon over m to the k. Well, this is equal to, well, just sum of the outer measures. There's really not much more you can do about that. But this adds up to a geometric series, the epsilon over 2 to the k, as you sum k equals 1 to infinity. Nothing special about the 1 over 2 to the k. Anything that adds up to 1 is perfectly fine. Okay, and this is for all epsilon positive. So just kind of summarize here, we have the outer measure of this union here we found to be less than or equal to the sum here for any epsilon. So therefore that means, well, what we want is true. It must be that the outer measure of the union is less than or equal to the sum of the outer measures. Okay, and that finishes the proof. Okay, so in the next video, we'll start building up more the basic foundational properties of outer measure, and in particular, we'll be able to start describing what measurable sets are, and then we'll prove some basic facts about measurable sets. Okay, and remember Wednesday, well, tomorrow, I'll go over the second bonus problem. The first bonus problem is just not really relevant to this course. Connectivity is not going to play a role. It's important, don't get me wrong, but it's just not really needed in this course. All right, well, so long, take care, until next time.